In this problem-solving screencast, we're going to look at converting a flat cyclohexane to a chair cyclohexane and doing a chair flip, where we're specifically looking at two diastereomers of 1-bromo 2-methyl cyclohexane, where we're treating with potassium hydroxide to do an elimination reaction. In an elimination reaction, we remember that the hydrogen and the leaving group have to be anti to one another. So when we're given a flat cyclohexane such as this, it's difficult to determine which hydrogen is going to get abstracted by the base. So if we label our carbon bearing the leaving group as the alpha carbon, we have to examine the beta carbons, which are the adjacent carbons, for the hydrogens present that are going to do the elimination. So in our two beta hydrogens, we can see that one has a hydrogen going down, and this other beta carbon has a hydrogen going down and a hydrogen projected up. So when we treat with base, we're going to abstract one of these beta hydrogens. In the flat cyclohexane, it's impossible to determine which one that is. So we have to convert the flat structure to a chair. So in our prior screencast, we saw how to convert a cyclohexane to a chair, and we're going to go ahead and do that now. So we draw our V shape, parallel bonds, and then our second remaining V shape. So here's our cyclohexane. Now I'm going to start with the alpha carbon, and I'm going to specifically put it on this carbon here. We can see that the bromine is projected up. On this carbon, it's going to be equatorial. And if we put in the other substituent, which is a hydrogen, it's going to be axial. If we look at this beta carbon, which is next door, it's going to be this carbon here. We can see that the methyl group is on the same face as the bromine. So for this carbon, it's going to be up or axial. And the hydrogen that's down is going to be equatorial. Let's go ahead and draw in the other beta carbon. Here it is. We have an axial hydrogen and an equatorial hydrogen. So in a cyclohexane, for an elimination to occur, the leaving group must be axial. So the bromine here is our leaving group, and we can see that it's equatorial. So therefore, that's going to necessitate a chair flip. So to do a chair flip, we're going to bring the carbon that's down, flip it up, and the carbon that's up, flip it down. So we're going to reverse our chair. Here's our V for the left-hand side of the molecule, our parallel bonds, and then our V for the right-hand side of the molecule. So there's our chair flip. Now any substituent that's equatorial is going to be axial. So I'm going to mark this carbon here now is this carbon. So the bromine is now going to be up or axial. Its associated hydrogen is going to be equatorial. This beta carbon, we have a hydrogen that's equatorial and a hydrogen that's axial. So I leave a space between this bond just to give it some depth here so we're not exactly crossing over this bond here. So in this beta carbon, the methyl group is axial, so when we chair flip, it's going to be equatorial. And now its hydrogen is going to be axial. So we have met the condition that our leaving group is now axial. So the elimination is going to take place from the beta carbon, beta, so we have 2 of them identified. And the elimination has to abstract an axial hydrogen. Well, if you look, both beta carbons have an axial hydrogen, which I've underlined. So each of these will be abstracted. So if we eliminate across this hydrogen here, that's going to give us the following product, and I'm going to draw it in a chair form. Parallel bonds. We're eliminating HBr across this carbon-carbon bond, so we draw in the double bond. This carbon still has the methyl group. This carbon has the hydrogen. So if we convert that to a flat structure, we end up with the following. So this is a tri-substituted alkene. Now if we eliminate the other hydrogen on the other beta carbon, we're going to end up with the following structure, and I'm going to draw it in a chair first, then draw it flat. So we're eliminating HBr across this carbon-carbon bond now. The hydrogens are going to be cis to one another. So we're eliminating HBr across here. We're in a 6-membered ring, so they have to be cis. We put in our remaining substituents. And if we were to draw this in the flat form, we have an alkene, H, so now we have a di-substituted alkene, and our methyl group is going to be up, so we're going to draw the wedge for that. So this reaction can produce 2 products when treated with potassium hydroxide. If we look at a diastereomer of this molecule, so what do we mean by that? The bromine is staying the same in terms of the RS designation. Now the methyl group is changing. So in this molecule, it's a trans relationship to begin with. We're treating that with KOH, and we're asked to determine the products. So it's important to draw this in chair form because it's not going to give us the same product distribution as the diastereomer. So let's go ahead and draw the chair. We start with our V shape. We draw parallel lines, and we end up with our V shape. Again, I'm going to put the bromine as up. So bromine is up. The axial hydrogen here is going down, which I've not drawn in. Our beta carbon here has the methyl group trans to the bromine. So on this carbon, if it's trans, it's going to go equatorial. And the hydrogen is going to go axial. So again, if we identify the leaving group carbon as alpha, carbons bonded to that are then beta carbons. We can do the same type of analysis in our chair. So we know that in an elimination, the leaving group has to be axial in a chair cyclohexane. So the leaving group is not axial here, so we have to do a chair flip. So we've drawn our V shape, we draw our parallel lines here, and then we end with another V shape. So here's our chair flip cyclohexane. I'm going to dot in, this is the alpha carbon. The bromine's equatorial. This carbon's up, so now the bromine's going to be axial. Its associated hydrogen is now equatorial. This beta carbon is next door here. The carbon is now down, so the methyl group is going to be down axial. The associated axial hydrogen is now equatorial. And there's this beta carbon. So we see that the leaving group is axial, but now on this beta carbon here, this hydrogen is no longer axial, it's equatorial. So the elimination cannot occur from this beta carbon. It has to occur from this beta carbon, which has an axial hydrogen. So this starting material is only going to give one product, and that product is going to be elimination across this carbon-carbon bond here. So that's the carbon-carbon bond that's going to get the double bond. So we're ending up with the di-substituted alkene. And if we draw that flat, here's our di-substituted alkene. The methyl group is showing as a dash, so it's down. So here's our major product from this diastereomer. So this has been a screencast on converting a flat cyclohexane into a chair, doing a subsequent chair flip for an elimination reaction.